Welcome to our glass plate. In today's example, we're going to take a look at skydiving. As you have probably seen in one of the movies, the students and professors had gone to a facility to do skydiving. And we would like to know how fast is the wind blowing around them in order to float. So our system, if we draw it, here is a human being. Well, not exactly, but a model of it. Basically a cylinder of diameter d and length L. In the suits we were wearing, an estimate of d would be something like 40 centimeters, and the length is about my height, 1 meter 80. We had to jump into, in essence, a wind tunnel, but a vertical one. Gravity is trying to pull us down, and we were floating because at high speed wind was blowing around us, giving an upward drag force. And if we literally float, that means that we don't move up or down, have a constant, almost zero velocity, so the sum of forces must equal to zero. Pulling down by gravity, being pushed up by the air flowing around us. And the question is, how big is this velocity? In the facility where we did it, they told us that the velocity was, in my case, 196 kilometers per hour. Now they can say whatever they want, but whether that's true is to be seen. In this exercise we're going to estimate whether that could be. Is it indeed this high a velocity, or are they exaggerating? How do we do that? Well, we need to model the drag force, and we know how to do that. It's a drag coefficient, it's a perpendicular area times half rho r v squared. V, the velocity of the air, the person itself is floating. If you use this, then we find that the velocity equals the square root out of 2 times mg over cd, a perpendicular rho of air. And here we're kind of stuck. We cannot compute the velocity because we don't know the drag coefficient. To find the drag coefficient, we need to look up the drag coefficient, which is a function of the Reynolds number. But we don't know the Reynolds number if we don't know what the velocity is. So this circles around. But the solution is pretty straightforward. We start up an iterative process. What we first do is we make a wild guess of what this CD will be. We anticipate that the velocity is high, the scale is relatively big, Reynolds numbers are relatively high, so the first guess is take CD order 1. That's not accurate because we don't know where we are, but it allows us to compute the velocity. And that gives 43 meters per second if you fill in all the numbers here and estimate my weight. Okay, out of that we can compute the Reynolds number, which is rho r, velocity of the air, a length scale, which is the diameter of the cylinder, over the viscosity of air. This is the same, it's 1.2 kilogram per cube. Viscosity of air, if you look that up, is 1.8, 10 to the minus 5 units is Pascal times second. So I can compute the Reynolds number, 1.1 million. Then I can look up for a cylinder what the CD is for this Reynolds number, and I find that CD is 0.4. I can recompute the velocity, I can recompute the Reynolds number, and I can find a new CD. And if you keep on doing this, eventually, and in practice rather quickly, you will arrive at the steady point. In this case is that we at some point in the iteration will find that the new Reynolds number gives a CD of 0.6. We compute a new velocity, which is about 200 kilometers per hour, and we get the same Reynolds number back. The Reynolds is then equal to that of the previous estimate. And thus the CD will be the same, and we found the solution. Okay, Conclusion. They were right. The velocity that you need to keep me floating in the suit that we were wearing is on the order of 200 kilometers per hour. Pretty fast. And you could feel that quite easily, and you can see it in the movie at my cheeks. Once we have understood how to model this, gravity balances drag force, we back out the velocity, see that we need an iterative scheme as we have two unknowns or one unknown function additionally. We start iterating with the known CD versus Reynolds number graph for a cylinder. Keep on iterating until you find the same Reynolds number or the same CD twice and you're done. Try it yourself. Estimate what your airspeed should be if you do it. Try it yourself if you use a parachute. How much should then the airflow be? And you will find out that obviously the flow of the air is quite a bit reduced. Good luck!